Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
So to kick this off, Linda, do you have any idea what those acronyms are?
CPU.
Yeah, you should know that one.
Core Processing Unit.
Uh-huh.
What was the other one?
GPU.
GPU. Something Processing Unit.
Well done. Well, it actually stands for Graphical Processing Unit.
Oh, see, I was close.
Yeah, you were very close. Do you have any idea what that might be for, why we have graphical processing units?
Visuals. To process visuals.
Do you know anything about why we need a special thing for visuals?
Well, visuals can slow down the computer, so I assume they want to do it quickly.
You know a lot more than I was expecting, actually. Do you know why they slow down the computer?
I don't know. It just takes up a lot of bandwidth to do.
Yeah, well, not so much bandwidth as there's just a lot of arithmetic to calculate. So think of where do GPUs come from? Like these 3D rendered games, right?
Mm-hmm.
You know, these really state-of-the-art games like Wolfenstein 3D and Doom 2.
Never heard of. Maybe Doom.
I actually thought you were going to call me out because those are old games.
Oh, okay. I wouldn't know old or new.
Well, I guess listeners now know the age at which I stopped playing video games.
Doom 2.
Hey, Doom 2 was really awesome when it came out. Back when shareware was still a thing.
Oh, I remember shareware. Oh my gosh.
Yeah.
Freeware and shareware.
That's
Whatever
right.
Did they die?
Well, they're just sort of unnecessary now. Or, I mean, the same spirit is there. But anyway, we
just don't call it that.
Yeah,
okay.
yeah, pretty much.
Let's talk about that
It's like data
day.
science. We've always had these things we call data science, but we didn't call it that until like 10 years ago. So the reason they invented the graphics processing unit is because the CPU was too slow to do the graphics. So they made a specialized thing that just focuses on graphics, because graphics do some specific things and they do a lot of it. So it's like a lot of trigonometry and just raw arithmetic, calculating distances and angles and stuff like that. So of course your CPU can do that, but your CPU does a whole lot more.
Right.
In the act of doing a whole lot more, it has a lot more complexity and it tries to cover a wider span of problems. And also, you know how many cores are on your computer and your CPU?
Mine's a quad core.
Quad core, all right, that's pretty typical. Your GPU, which you don't have a GPU, but if you did, it would guaranteed have way more cores.
So wait, why don't I have a GPU? How am I supposed to see visuals?
With your monitor, you don't need the fast rendering and stuff.
Not every computer needs a GPU.
No. Mostly, so here's the interesting part. A long time ago, I would have said, oh, you only need that if you're like a hardcore gamer playing these like 3D games, maybe like StarCraft and stuff like that. I don't even know what needs it because I'm kind of out of the gaming world. But I would say you only need a GPU if you want really fast, high frame rates on these complex textured games.
I don't know. You're telling me.
Yeah, I am. That, in theory, was the only reason you needed a GPU, and that's why they were called the GPU. But then some very clever people realized, hey, wait a minute. That thing that has all those cores and can do simple stuff, just some simple arithmetic and matrix operations are really, really fast for the purpose of games, that can be jerry-rigged to do calculations for scientific computing and for machine learning and other stuff like that. So they came up with these interfaces. The earliest one I remember playing with was something called CUDA, where you could connect to your GPU, which normally only graphics went through, and send it just really hard math problems to solve. And it would solve them really fast. For one thing, it had a lot more precision in terms of higher floating point numbers, but it also had way more cores and it could parallelize problems really well.
Did you say floating numbers or flowing?
Floating point numbers.
What are those?
A floating point number, well, that's actually a complicated topic that's getting a little bit outside of the data science area of things, but basically it's to give you the high level answer, it's any number with a decimal.
Oh, how come I didn't learn that in math?
It's more of a computer science-y thing. Mathematicians, they think about continuous numbers usually. And I mean, they know the difference between a real and a rational number, but they don't care about it the way a computer engineer would. So now we have this tool, a GPU, and for some reason we still call it GPUs, even though I think it's being used more for non-graphics than graphics if you really calculated it for all the GPUs in the world.
So people buy them specifically to do these math problems?
Yeah, and specifically, the reason we're talking about it is because it's very common in deep learning. So deep learning is often heavy arithmetic steps or, calculations that are done many, many times, many iterations, and you want to speed that process up. So people will buy not just one GPU, but they'll buy banks of these things often and put them in a rack. If your problem is not that tricky, You might be able to solve it with your computer's CPU or some cloud-based CPUs, but it will take you a lot longer, to converge. So the same number of iterations might lead you to the same answer.
So why is the CPU slower?
Essentially, it's because there's a lot of choices they made in architecting the CPU, and it's aimed at doing good performance on your average everyday computing. I don't know if this is true anymore, but I remember in undergrad, someone told me that 25% of the time computers are working, they're just sorting things. And that's actually believable. If you're doing a lot of sorting, you want a machine that's good at sorting. And if you're doing a lot of other tasks, like general purpose tasks, which are what CPUs are for, so a CPU has to be able to run basically any program you throw at it, right? You would be very upset if you found out your computer couldn't run some piece of software for no good reason, right?
Sure, that happens when I buy something and then I didn't pay the license. So.
Well, that's a different problem.
So that happens all the time. Not related to my CPU.
That's correct, yeah. We've talked about, you know what coding is, right? You know what people write in code.
Yeah.
Coding is actually, there's kind of a layer cake of things below it. Like if you write in Java, beneath that is the Java virtual machine that's giving you certain functionality. And beneath that is, I don't know if it's written in C or whatever it is, which is a programming language. And beneath that, everything goes down to assembly language. And assembly language is this very sort of pedantic. No one really writes assembly. They might write a few lines to optimize some very specific bottleneck. It would be like if I gave you a recipe for how to make an omelet, and it was a book that had like 400 pages, and it described like how you should move. Instead of saying flip the omelet over, it described how you should turn your arm and the angle at which you should push in the spatula, and details so pedantic that you can almost not even do the task. That's what like assembly language is. Some very smart people have tried to make CPUs faster by doing things like pipelining.
So what's a pipeline?
So pipelining is kind of cool. It's where you anticipate what the next instruction might be, and you preload it, and you get ready to execute it because you assume it's coming next. And if you're wrong, maybe you wasted a little time. But if you're right, you can make the program go faster. So there are all these really clever optimizations that in general help programs run faster. But for very specific tasks, like you want to multiply two really large matrices together, that doesn't describe all of computing, but that's a common task, especially in machine learning and stuff like that. The GPU can be specialized in just that matrix multiplication operation or the components of it. When you can define your program in terms of these algebraic vector operations, you can push them to the GPU and they'll run, usually the ballpark number I hear people say is about 10 times faster, give or take. Your mileage may vary. We've talked about gradient descent before. Gradient descent is you iteratively come up with an answer, see how well it's doing, and you move in the direction that seems most correct, and then you check again and repeat. So that process just takes time. You just have to repeat that. And other such optimization steps that aren't able to be solved with exact solutions sometimes require just brute arithmetic to get them done. And the GPU can do that faster. GPUs, in this weird way, have now outgrown their original purpose, and they're used very heavily in a lot of machine learning, and especially in deep learning. There are certain problems that are kind of intractable without GPUs.
Do all data scientists use GPUs?
Well, certainly not all of them. And in fact, not even the majority. I would say you use it if you have a problem that is of enough, scale or complexity. One of those words is correct, maybe both. Generally, the problems that GPUs are helpful for are deep learning packages, not only because that's when you need that sort of speed and they're appropriate for the types of problems you're solving, which are these massively parallel type problems where you're solving each, neuron's optimization at every step individually, and you can take advantage of the fact that the GPU has sometimes hundreds of different cores. But also there's just something about the complexity of the problem and how long is feasible to wait for an answer. So I run a lot of models that might take 4 or 5 hours to compute. And yes, I could make them go faster on the GPU, but it's kind of like, who cares? I'll just, run it and come in tomorrow morning and it's ready. A lot of it, I think, has to do with whether or not the frameworks are set up for it. So if you use something like TensorFlow, which is a very popular deep learning software, it's already set to run on your GPU. There's just a very tiny configuration you have to set. Whereas if I wanted to run, an algorithm that's not as popular or doesn't have that configuration, I'd have to build my own library. So then I'm either, an open source contributor starting my own project, and I have enough projects, or I just find another way. But I think eventually everything will have the right access to GPUs, and probably there'll be some behind-the-scenes optimizations that make these choices for you.
So how do people learn how to use GPUs in this way?
How did people get the idea, or how does one go and do it?
How did you learn?
I first heard about this actually from our friend Doug. Doug was doing this on a project. He was saying something about they needed to get higher performance. They'd been looking at parallel stuff, and then they'd found CUDA, which I later used, which was a way to tap into the machine's GPU. And right away, it made perfect sense to me. It's one of those things where it was like, oh, I should have thought of that. But if you have computations that are a good fit for the GPU, then putting them there to compute is way better.
So you just learned it from experience.
Yeah, I learned it from hearing what other people were doing. All right, so that's the whole GPU, CPU thing. GPUs offer a specialized type of calculation that is massively parallel because it has so many cores and optimized for speed on those calculations. So that's what's really enabling certain things, especially deep learning, to be practical. Well, thanks as always for joining me, Linda.
Thank you, Kyle.
And until next time, I want to remind everyone to keep thinking skeptically of and with data. Good night.
Good night. Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.